All right. Welcome, everybody. I'll wait just a few minutes uh, in case people want to join. And while we're waiting, I just have some quick announcements. First of all, hi, my name is Ryan Jacobs. I've been a teacher with Manhattan Prep for 14 years now, teaching the GMAT the whole time, a little bit of SAT and other stuff as well, executive assessment. And welcome to our free GMAT Prep Hour. Today is June 10th, 2025, unless you're watching on YouTube, in which case it's a later date. But the GMAT is probably still testing this stuff as it has forever and ever. Before we get into the actual topic of today, I want to mention a few other free resources that we offer here at Manhattan Prep. And if you want to just Google these search terms, you'll be able to find it. But the first one is a free GMAT starter kit that'll kind of teach you a little bit about the test. It's downloadable, and you can peek through that. We also offer complete courses, and those are paid courses. They're all 9 sessions. But one nice open secret is that the first session of the 9 sessions is offered for free. So if you want to come try out a class, it's actually really cool because in the first session, we'll teach you about the scoring algorithm and a little bit about a couple of the question types that you'll see on the GMAT. So it's really useful. I mean, we're going to get right into the content of the course. And I have one coming up at the end of June, and another one, a weekend course starting in July, if you prefer to do it on Saturdays. And there are plenty of other teachers at Manhattan Prep who are all great as well. So, try out a couple different courses if you want, see which teacher you jive with best, and check that out. And then finally, one of my favorites is Manhattan Prep offers a free Foundations of GMAT Math online course. And I believe there's one starting this Saturday. We run them fairly often too, so you can just search for this search term and you can go find it. And that course is really great because it'll teach you the basic math that you're going to need to know for the GMAT. So if you are studying and it's been a few years since you were in college, or you feel like you never really learned algebra all that well in high school, this is a really great course and it's free. So check that out. Um, so today I wanted to just go over some special topics in exponents, is what I'm going to call it. And I'm sort of presuming that you know a little bit of exponent math, but if you don't, that's okay. Feel free to ask questions in the chat or in the comments if you like, if you're watching this later. But there are a few things I've noticed teaching a lot of classes about exponents that people tend to have more trouble with than other topics. So I wanted to show you a few of those today and just go over how to deal with those special situations when you find yourself in them when you're going through the GMAT. So first one I want to bring up is this one. Simplify 4 over root 2. And if you're watching this later on, feel free to pause the video now if you're watching the recording and just try to attempt this yourself. Otherwise, if you're watching live, I'll show you why this needs simplification, first of all, because I don't think it's all that obvious, actually. For some reason, a long time ago, a bunch of math nerds got together and decided we don't like it when there's a square root on the bottom of a fraction. So they called it an irrational denominator. It's irrational because the square root of anything that's not a perfect square is going to be some random number, right? Some long decimal, something like that. And we don't like having that in the denominator. So they said what we need to do is rationalize the denominator. Now, I'm only telling you that name because if you want to look it up later, maybe in one of your textbooks or something, this is what the process that we're going to do is called. All right, we're going to rationalize this denominator. And the way we do that is by thinking, what do I need to multiply the denominator by to make it rational again? So in this case, we're going to take the 4 over root 2, and we're going to multiply it by the square root of 2, right? We're going to multiply the denominator by itself, but we need to do square root of 2 over the square root of 2 so we don't change the value, right? So if you multiply it by basically a fancy form of 1, you're not going to change the value of the fraction. but you are going to rationalize the denominator. So on top, we get 4 times the square root of 2. But on the bottom, we get root 2 squared, which just works out to 2. So now you can see we can simplify this. 4 divided by 2 is 2. And so we have 2 root 2. So it's okay to have a square root, right? That happens sometimes. We're just not allowed to have it on the bottom of the fraction. So that's why this final version is considered simpler. Okay. So every once in a while, the GMAT will ask you to rationalize the denominator. And now I want to give you an example that's a little more test-like. So take a look at this one. I'll give you a minute, see if you can solve it. Oh, hey, it's the wrong one. So we'll get to that other one later. Try this guy. Okay, so you might have run into a little trouble here because if you tried the same trick that we used last time, where you take this 6 plus root 5 over 2 minus root 5, and you just multiply the denominator by itself, 2 minus root 5, this is not going to work, as you probably found out if you tried it. Because when you FOIL this out, right, you take this times this guy, you're going to still end up with a square root, right? You get 2 times 2 is 4. Then you get minus 2 root 5, and then minus another 2 root 5, so minus 4 root 5. And then you get plus 5. So this is a problem. We haven't rationalized the denominator. So let's back up a bit. And we have to think, what do I need to put on the bottom of this fraction so that it becomes rational? And the answer here is 2 plus root 5. Now, when you have a minus sign or a plus sign here in the denominator of the fraction, and you have something that's irrational, if you change that minus to a plus, this version of it is called the conjugate of this. And I'll type that up. And again, this is not a term that you need to know for the GMAT unless you want to like look this up in a textbook somewhere. But we're multiplying by the conjugate. And what happens, you'll see, if you're familiar with this A minus B times A plus B template, you might remember that that ends up equaling A squared minus B squared. And so when I multiply by the conjugate, I get 2 squared is 4 minus square root of 5 squared is just 5. And the square roots go away. So that's what I want, right? I want a rational denominator. I want to get rid of all the square roots on bottom. And this is what's going to do it. So up top, I just need to FOIL all this out. So 6 times 2 is going to get me 12. And then plus 2 root 5 plus 6 root 5. So that's plus 8 root 5. And then finally, root 5 times root 5 is going to be plus 5. All right, so now we're in business because that top of the fraction is just 12 plus 5 is 17 plus 8 root 5. And then on the bottom, 4 minus 5 is negative 1. So just make it negative. You got negative 17 minus 8 root 5. And that is answer choice D. All right. So like I said, I've seen this give people a lot of trouble on the GMAT when they have an irrational denominator that's got a plus sign or a minus sign in there, right? People tend to have an easier time with the first example I gave where it's just one single square root. Oh, you can just multiply it by itself to rationalize it. But you want to practice also rationalizing denominators that have two terms. And the way to do that is by multiplying by the conjugate. So you'll see this from time to time on the GMAT. You can practice it when it comes up. Last thing, though, that I want to point out about this particular question, I don't know if anybody out there solved it this way, but you could sort of estimate because the square root of 5 is definitely more than 2, right? Square root of 5 is about, call it 2.2, maybe 2.3. So up top, you're going to have a positive number. And on bottom, you're going to have a negative number, right? Because 2 minus 2.2 is definitely going to end up being negative. That gets rid of answer choice A, gets rid of answer choice C, it gets rid of answer choice E. And I'm guessing that this is not an integer. You know what I mean? I'm guessing it's not going to work out so nicely to negative 17. So you can kind of estimate that the answer is D for this particular problem. Little reminder that even if you're not sure how to do the algebra, not all is lost on the GMAT. So. Cool. So that is our first special topic in exponents, is rationalizing the denominator. All right, let me show you the second one. I'm going to back up to the one that I skipped earlier. And I'm just going to give you a couple minutes to look at this problem on your own, see if you can solve it. Then I'll tell you about what topic we're looking at. Okay. So here's another one I've found that throws people for a loop sometimes, is when you have the variable up in the exponent here, and you are constrained to integers for that exponent. Because this looks kind of unsolvable, right? We only have one equation and we have two variables. But in fact, this integer constraint actually makes it solvable since there's only going to be one pair of numbers for m and n where they're actually integers, right? If we can't use fractions here. So I'll show you how to work this out. We're going to keep the left side the same, 2 to the 18th times 5 to the n power. And we're going to use an exponent rule that I think gets a little bit forgotten, which is 20 to the n power is the same as saying 10 to the n power times 2 to the n power. So the exponent rule here is that like if you have x times y to the z, you can break that down into x to the z times y to the z if you want a generalized form of this rule. But the idea is that you can take this 20 and whatever multiplies to 20, you can sort of break it apart that way. And you can do this any way you want. So we're going to start by doing exactly how I suggested. I'm going to take that 20 to the n, and I'm going to say it's 10 to the n times 2 to the n. But you might notice I can break it even further. So 2 to the 18th times 5 to the n is equal to 10 can be broken apart further, right? So I'm going to call that 2 to the n times 5 to the n. And then don't forget the other 2 to the n. And now, finally, I'm going to take this 2 to the n times 2 to the n, and I'm going to use that exponent rule to combine those terms. So I get 2 to the 18th times 5 to the m is equal to 2 to the n times 2 to the n is going to be 2 to the n plus n, or 2 to the 2n. And then times 5 to the n. All right, so we've made some progress because notice now, instead of like 2 and 5 on the left side and 20 on the right side, we have 2 and 5 on the left, and we also have 2 and 5 on the right. And that's always your goal with these problems when you see those variables up in the exponents, is you want to get it so that the left side looks kind of like the right side. We've done that. The reason for that is, this is where it gets fun. If m and n have to be positive integers, well, 2 and 5 are totally different prime numbers, right? So that means whatever this is has to be equal to this. That's the only way that we're going to make m and n both equal to integers. So I can just say 18 equals 2n. And by the way, I can also say m is equal to n at this point, right? Whatever those powers of 5 are, they got to be the same on both sides. Same for the powers of 2. So I'm going to write 18 equals 2n, and I'm also going to write m equals n. So now we're in business, right? Divide both sides by 2, you get 9 equals n. And so if n is 9, then so is n, because they're equal. So what is the value of m? It is equal to 9. Cool. So if you thought that was fun, I got one more. This is kind of a variation on the same problem, but it's got a little bit of a wrench. And I'll even just highlight the wrench so you can consider this. This doesn't just ask you for whatever the number is, it asks you for the sum of the digits of this product. So basically, you're going to have to think about this number, like if it were written out as an actual number. What would the sum of all the digits in that number be, right? If I took every single digit and I just added them up. See if you can figure it out using some of the tricks that we've learned already. I'll give you a couple minutes to work. Okay. So were you able to solve this one? This one is really tough, probably the toughest we've done so far. But what's cool is it uses the same principle as we just saw in the last problem. I'll show you how. So the question asks us about 3 times x times y. And I'm going to start just with x times y. We'll do the times 3 at the end. But if I multiply x times y, I get 2 to the 25 times 5 to the 21. And at first glance, it kind of looks like there's nothing I can do, right? Because the bases are different prime numbers and, no common factors or anything. So I can't do anything with the 2 and the 5. And then the exponents are different as well, right? This is 2025, and this is 2021. So I can't do anything yet, but what I can do is separate the 2 to the 2025 into 2 to the 4th times 2 to the 2021. And then I'm going to keep the 5 to the 2021 the same. So I mentioned earlier, one of the problems we had was that these exponents were different. And so the reason I'm doing this step is because now these exponents are the same, right? And now I can be productive. So that's why I split it apart in this particular way. And an interesting thing here, I've noticed with a lot of my students, they have an easier time being presented this and knowing that it's equal to this than the other way around. Most of my students have a harder time being presented with something like this and remembering that you can split it apart. So it's a nice reminder that whenever you're doing algebra, it goes in both directions. You know what I mean? And if you can become really proficient manipulating it both ways, that's a really strong way of studying is to really, be so solid on your exponent rules that you can use them to your advantage no matter what you're presented with. So you can probably see a little bit where I'm going with this. Now that these exponents are the same, I can combine them using that same rule from before, albeit in the opposite direction. This is equal to 10 to the 2021 when I multiply these together. And what's nice about that is 2 to the 4th isn't so bad to calculate. I can just do 2 times 2 is 4, times 2 is 8, times 2 again is 16. Or you can just memorize that one. And if I multiply that by 10 to the 2021, that's just going to be multiplying by 10 2021 times. So this number is 16 gazillion, billion, million, quadrillion, whatever. It's just 16 with 2021 zeros after it, which means the sum of the digits is going to be 1 plus 6 plus 0 plus 0 plus 0 plus 0, right? But don't forget, we're interested in the product 3xy. So I got to take this thing, I got to multiply it by 3. And the GMAT's actually being really nice here and not giving us 7 as an answer choice. Might have trapped a lot of people. But 3xy is going to be, let's see, 16 times 3 is 48. So 48 gazillion, billion, quadrillion, million. You get the idea. So what is the sum of the digits? It is 4 plus 8 plus 0 plus 0 plus 0 plus 0 forever and ever. So 4 plus 8 is 12. Correct answer is B, and we are done. All right, so just to recap these two issues, the first problem, or the problem we did just before this, we had variables up in the exponents. And the trick was to make the two sides look the same. Here, this problem shares one other similar trait, which is we've got 2s and 5s that become 10s. And so anytime you see a 2 to the something and a 5 to the something in the same problem, be suspicious that it might really be about the zeros you're putting at the end of the number. I've seen this a couple times, and it throws people for a loop when it pops up because, I think it's a little less commonly tested maybe than some of the other stuff, but now you know. Now you're ready. All right. So we've covered a couple special topics in exponents. I'm going to switch gears here, and I'm going to show you another one. Take a look at this problem. This problem can be solved in a couple different ways, by the way, so do it any way you like, and then we'll chat about your options. Okay, so the most important thing I can probably tell you is don't pick answer choice D. Because 150 minus 96 is in fact 54. But the square root of 150 minus the square root of 96 is not just the square root of 150 minus 96. So it's not the square root of 54. And you kind of knew that deep down in your heart. Right. So you know D is the trap answer. And in fact, I have a running joke in my class that every time you make this particular mistake, a puppy goes to jail. Sad. Oh no. In fact, this mistake is so common that I used to keep this little puppy in my classroom. And I had a little jail cell that I had made specially for him. And so if anybody made that mistake, he would go in the jail cell until they corrected the mistake. And by the way, this puppy's name is Factor because the way to avoid making this mistake, if you find yourself in this situation where you need to subtract square roots or exponents, is to factor. So that's our goal here is what can I factor from 150 and from 96 to make my life a little bit easier. Um, so my advice is to look for something that they have in common. And in this case, what they have in common is the number 6. So 150 is 25 times 6. I'm going to factor it out to that. And then 96 is, let's see, 6 times 15 would be 90. So that's 16 times 6. And now you can see we're in business because I can't just split exponents or square roots apart when I have subtraction or addition. And I can't just smush them together, but I can do that when we have multiplication. So root 25 times 6 is in fact root 25 times root 6. And that's where the confusion comes from, I think, is people forget that the same rules for multiplication and division don't carry over to addition and subtraction. Make sure you know the difference when you're studying your exponent rules. But this is certainly a lack. So you get that over here. I get root 16 times root 6 over here. So that would be 5 root 6 minus 4 root 6, which is just equal to 1 root 6. That would be answer choice A, and we are done. So don't be fooled. D is a trap. Instead, factor it out. You'll find A is the correct answer. Now, before we go on, some of you may be laughing into your camera because you're saying, ha ha ha, Ryan, I was done in about 5 seconds while you were doing all that. To which I would say that's awesome. You probably had the right idea here because some of you might have noticed you can also just estimate the answer. And this is another big topic with square roots in particular that I wanted to go over today. Is you should know your perfect squares. So 1 squared is 1, 2 squared is 4, 3 squared is 9, etc. Right? 16, 25, and so on and so forth. And if you know your times tables pretty well, you'll have these memorized already. But it's nice to recognize them. And I'll show you why. Let me go a little further, actually. Sorry, that's not 5 to the 5th, that's 5 squared. I'll go a little further, actually. 6 squared, 7 squared is 36 and 49. And then for this problem, 10 squared is going to become relevant. So that's 100. And also 12 squared is 144. So I'm skipping ahead a little bit. But the reason is I'm looking at square root of 150, and that's like a little more than 12 squared. So this is probably something close to, call it like 12.2, 12.3, something like that. And then 96 is a little less than 100. So this is like, 9.8. So it's basically 12 minus 10 plus a little more. Call it about 2.4. Now I can look at the answer choices, and then square root of 6 is a little more than 2 squared. So yeah, 2.4, maybe 2.3, I'd call it. Square root of 12 is more than 3, so maybe 3.3. Square root of 20 is bigger than that. D is bigger than that, and E is way bigger than that. So what's the closest to 2.4? Well, that would be answer choice A. So if you get really comfortable just sort of estimating square roots like this, a lot of times the GMAT is going to reward you for that. And solving problems by estimation, I think this is kind of my opinion talking, but I think it's the most underrated strategy on the quant section of the GMAT. Just estimate. If all they give you is numbers, even if you don't get all the way down to the answer, even if you're like, down to two answers, you're still doing it really quickly. And remember, on the new version of the GMAT, you can always go back to that question later and check your work if you have time to do it. So you can sort of hedge your bets by just like estimating and moving on. And then at the end of the section, go back, see if you did it right. A little time management strategy for you. Okay. So we had one of these problems where we had to factor. Let me show you a more complicated variation of this same idea. Give this one a shot. All right. So hopefully this one was a little easier for you after the last one we did. Um, and in case you ran out of time or you ran into trouble here, let's just go through it together. The first thing I'm going to tell you is when I solved this problem the first time, my first step was to write 9 to the 5th over 7 to the 3rd divided by 9 to the 7th minus 9 to the 5th over 7 to the 5th plus 7 to the 3rd. So essentially, I'm just writing Q over P on my scratch paper as is without doing any math. You might be better than me at doing math on the fly and like rewriting it, but I know myself and I'm going to mess it up if I try to do that. So I just like to copy it when it's something this complicated onto my scratch paper as is, so I don't like mess that part up. That for me that would be the worst way to miss the problem. So once we have that, right, we want to know what this is equal to. now we can think, okay, how do we solve this? And I'll just show you again. The GMAT, I think, is trying to trap you into saying that this is 9 squared, which it's not, right? Don't send any puppies to jail. This is not 9 squared, and this is not 7 to the 8th. So what do we have to do? We got to factor. So how do I factor that bottom? Well, I need to find a term that they have in common. And in this case, that's going to be 9 to the 5th on the top, and it's going to be 7 to the 3rd on the bottom. And so now you just have to think, well, what would I need to multiply 9 to the 5th by to end up with each of these things? And the answer is going to be 9 squared, right? 9 to the 5th times 9 squared does end up with 9 to the 7th. And then times 1 to get back to 9 to the 5th. And likewise, we're going to do 7 cubed times 7 squared to get back to 7 to the 5th, plus 1 to get back to 7 to the 3rd. And the top of the fraction just stays the same. Well, now we're in business because 9 to the 5th divided by 7 to the 3rd is on the top of the fraction, and it's also on the bottom of the fraction. So it's just going to cancel out, and I'm going to get 1 over this. So I end up with 1 over 9 squared is 81 minus 1. That's 80. 7 squared plus 1 is 49 plus 1. That would be 50. So 1 over 80 50ths is the same as 50 over 80. That reduces to 5 over 8. Hope that's an answer choice. It sure is. Correct answer is answer choice C. And be a little careful here. The most commonly picked wrong answer is answer choice D, which is just brutal, right? Because that means you've done most of the math correctly. You just kind of forgot to flip the fraction or something like that. But C is the correct answer. So nicely done if you were able to factor that out. Notice we are factoring in a different way than we did before with the root, but the solution was still the same. Anytime you have an exponential set of terms, separated by a minus sign or a plus sign, try factoring it out. Anytime you're dealing with square roots or cube roots or something, and you've got a plus or a minus sign to deal with, try factoring something out or finding a common factor. Nice. So I think you're ready for our final topic in exponents, special exponent topic. This one is a real doozy. I think it's the hardest problem that we've seen today. But I'm going to give you some time. Really, use whatever strategy you can throw at it. And I will tell you there are a couple different ways you could approach this, a couple different ways you could solve this. So give it your best shot, then we'll chat. Okay. So before we get into the math on this one, I'm going to take a step back and I'll tell you guys a little something that I talk a lot about in my course whenever I teach GMAT Quant. I think, there's a number of students who come to my class and tell me some variation of, man, Ryan, I was pretty good in college. I got good math grades. I actually kind of like math, but for some reason, I just can't do standardized tests. So like SAT or, whatever other standardized test they took in their life, or the GMAT, when they get to it. They're like, for some reason, these just get me. And I've thought a lot about that. I sort of feel like one of the major differences between your college tests and standardized tests is that standardized tests more often are multiple choice than college tests, where you're supposed to solve top down and show your work. And there are a number of strategies that you can use when you have answer choices available to you that you can't use when you have just a regular top down test. So we're thinking now about top down approaches or approach, uh, i.e. do the algebra / the textbook approach versus approaches that are multiple choice specific. And one of the big ones that we've talked about today that we're actually going to maybe even use here is estimation. There are a couple others, and if you've studied for the GMAT for a while, you may be familiar with some of these already. You can pick numbers, or pick smart numbers, some people call it, or you can work backwards from the answer choices. The main difference between those is picking numbers means picking your own numbers that are coming from your brain, whereas working backwards is picking the numbers that are already in the answer choices. Those are the big three. That said, there are a couple others, like solve a simpler version of the problem, or what we're going to do here, which is look for a pattern. And there are some others too, like draw a picture. We could go on and on. But the way I solved this was to look for a pattern and also to estimate a little bit. So I'm going to show you how that worked in this context. First of all, we've talked about a lot of square root approximations, but I want to give you two specific ones that I found really useful, and that is the square root of 2 is about 1.4. The square root of 3 is about 1.7. And we're going to use those pretty heavily as we go through this. But if you want a way to memorize them, I'll show you a neat little trick. Valentine's Day. Never know where the apostrophe is. I might have gotten that wrong. Whatever. I know when it is February 14th. And St. Patrick's Day is March 17th. So you can use those holidays to help you memorize the square root of 2 and the square root of 3 approximations. One of my favorite little mnemonic devices for GMAT study. Anyway, first time I saw this problem, I had no idea how to do it algebraically. So I just switched my strategy. I was like, let's say we didn't have an infinite number of roots. Let's just say we had root 2 or root 2 plus root 2. Well, that would be equal to root 2 plus 1.4, be equal to root 3.4, which I know is a little more than 1.7, right? Because root 3 is 1.7, so this is maybe 1.8. Cool. Well, let's extend it a little bit. What if we had root 2 plus root 2 plus root 2, right? What if we have 3 of them? Well, check this out. This is the same as what I had up top. So I know that that's just 1.8. Right. So that's going to be root 2 plus 1.8 approximately. So that's about root 3.8. Well, that's getting really close to 2, right? So what do we want to call it? Like 1.95. So let's do this one more time. Root 2 plus, let's say we had 3 of them, right? 2 plus root 2 plus root 2. Sorry, it's getting a little hard to write. I think you get the idea. Well, now all this stuff is the same as what I had up here. So I can just call that 1.95. Right? So that's root 2 plus 1.95. That's about equal to root 3.95. And now I can kind of see what's going on, right? That's really close to 2. That's going to be 1.99. And I think if I did it forever and ever and ever, it seems like I would end up with 2. And it turns out that B is the correct answer. So first time I saw this problem, that is exactly how I did it because I had no idea how to do it any other way. So again, one of our special situations in exponents that I was talking about earlier is if they just give you numbers, right? There's no variables in this problem. Consider estimating. Consider that you might be able to get to the answer just by sort of approximating what that value is going to be. And in fact, you can do it here. Correct answer is B. That said, I did look up the explanation later. And in case you were wondering, all the problems I picked today are either written by Manhattan Prep or they were written by me specifically for the session to torture you a little bit or to teach you something. But this one was from the Manhattan Prep Advanced Quant book. So I looked up the explanation because I was stumped. And here's what they said. They said, you can actually say x is equal to this thing, right? Root 2 plus root 2 plus root 2 plus root 2, et cetera, forever and ever. And what you can do then is square both sides. So you're going to end up with x squared equals 2 plus root 2 plus root 2 plus root 2 forever and ever. But in doing that, you've introduced the same thing you had before, but in a different way, right? So these two things are equal to each other, which also means this is equal to x, right? Since those two things are equal to each other. And so now, all of a sudden, I end up with x squared equals 2 plus x. And I've managed to use substitution without ever having an equation, which is just bending my mind. So if it's bending your mind too, like, don't worry about it. First time I saw this, I was like, what is going on? But that's how we can get rid of this infinite expression, which is really the problem here. So at this point, it just becomes a good old quadratic. X squared minus x minus 2 equals 0, right? Solving quadratics, we always need a 0 on one side. And so I can factor that out. I'm going to get x and x. And let's see, if I'm multiplying to -2 but adding to -1, that's going to be x plus 1 times x minus 2 equals 0. So therefore, x is either equal to -1 or x is equal to 2. But since you have a radical sign here, radical means it's got to be positive. That's implied. You can't have imaginary numbers or anything on the GMAT, nothing weird like that. So -1 is not the solution. It's got to be 2, and B is the correct answer. So this explanation, by the way, is not part of my exponents lecture for today. I just threw it in on the side because I thought you might get a kick out of it. But really, the main takeaway from this problem is if you can't do it algebraically, try estimating, especially when you're working with square roots and it's just numbers. There's no variables or anything. Estimation is always a trick you should have up your sleeve. Cool. So let me go back and wrap this up. Again, thanks for joining me today. My name is Ryan Jacobs. I am a teacher with Manhattan Prep. I've got a couple courses coming up. There's a Monday and Wednesday night class I'm teaching starting at the end of June. And then there's a Saturday morning course starting in July, I think mid-July. And if you want to find out where those are, just go search for Manhattan Prep GMAT Complete course. You'll see my classes along with the classes of many other great teachers at Manhattan Prep. So feel free to come to our first session of any class. It's free. You can meet us. You'll learn a little bit about the GMAT scoring algorithm. You'll learn a little bit about data sufficiency, and it'll just be great to see you there. So yeah, thank you guys so much for joining me. I hope you learned something a little further about exponents, and I hope it's useful to you in your studies for the GMAT. Good luck. See you later.